Hey y'all, welcome back to Alakazam Math Made Easy. In this video, we're going to go into the use of derivatives to find rate of change, right? So that's why I've been over this a couple times. That's why derivatives are super helpful, right? Because they allow us to interpret the rate of change of any function, the instantaneous rate of change at any function, at any point we want to look at, right? Just by plugging in an x value to that same function. So just to go over a quick review, there's two different types of rates of change. Remember, the first one being the average rate of change, and that is related to the secant line. And remember, the secant line by definition has two different points of contact with the function you're looking at, right? So how should I remember that? Well, first of all, if you haven't memorized it from your limits section, let's cover it now. But second of all, it goes back to the definition of average, right? If I'm taking the average of several numbers, right? I'm going to add them up and divide by however many numbers I'm doing, right? So it's going to be, let's see, 1 plus 2 is 3, 6, 10, 15 over 5 is 3, right? But the premise is that I'm adding these all up and I'm looking at the average of the values between 1 and 5. They happen to be counted by 1, but what I'm doing is I'm looking at the average of the values between 1 and 5 here. Graphically, a secant line does the same thing, right? I'm looking at the average of the function values between x equals 1 and x equals 2. So that's how you should know that the average rate of change is a secant line, because it covers the function over multiple x's, right? And I can draw however many x values I want in here. It'll accommodate that because I'm asking for the average between outside the x values that outside of that range. So that's a secant line. But what happens if I don't want to know an average? I want to know something much more accurate. That's the instantaneous rate of change. Remember, that's associated with the tangent line, which is different from the secant line because it only comes in contact with the function at one point. So I've always said you can imagine that by saying I'm going to take this red dotted line and push it up against the function until it barely touches it, right? So that's that. And again, this is instantaneous because if I'm only looking at this one x value, it has to be associated with that instantaneous rate of change. So practically, how can I use a derivative, right? Practically, because this is a graph we've seen now 3 times, I believe, because this function is so curvy and whatnot, the function derivative changes anytime you change the value of x, right? And that's a situation that's very common in real life. So what we're going to end up doing is we're going to look at how we can use the equation for a derivative, right? The principle of a derivative that results in the equation of a function. We're going to use that to find any value of x. And I think I gave a little bit of a spoiler alert in a video in the past, but this function, this relationship is something that we've been over before, right? So the instantaneous rate of change can actually be defined by a function, and then to find an instantaneous rate of change at a specific x value, you just plug in whatever value you want into that derivative function. So let's do an example, right? So here, find the instantaneous rate of change of this really long polynomial at x equals 3, right? So the first thing we're going to do is take the derivative of this. This is y. We need to find y prime. So this is y prime. So find the derivative. So now we have that, right? That 33x squared plus 2 shows us that regardless of what x value I plug in, it'll have that slope at that x value, right? So again, real quick, we found the 33 by doing 33 times 11. X squared is from x cubed to the minus 1. We found the 2 by saying 1 here distributed over that 2. And then the 1 minus 1 ended up being 0, which means it's not there. And remember, for a constant, you can approximate it as that number times x to the 0. We multiply the 0 to the front. It doesn't matter what the exponent is doing because we've now multiplied 0. So that's where this comes from. So now what do we do? So we have the function, but when we want to know what the actual rate of change is at x equals 3. So that's why we plug in 3 for the x value of that function. And basically this is all just simplification to our answer. So basically what it's saying is that 11x cubed plus 2x minus 3, if I'm looking at just the x value, x equals 3. So it'll look something like, I'm sure of that, right? And then 3 is probably somewhere like here. So the rate of change at this point is 299. The slope of that tangent line is 299 at x equals 3. So that's what that tells you. Let's do a problem together that's a little bit more complicated, right? Because here we have a function that has two functions being multiplied together, which means we use product rule. Remember, product rule is, as I'm writing here, the first function, the derivative of the first function times the second function times the first function times the derivative of the second function. I'm sorry, plus the first function times the derivative of the second function. So that's by definition product rule. And you can look at video, I believe it was 12, to go over that more. In terms of this problem, we'll go jump right in. So 2e to the x, that's our u. That's going to stay the same because we're taking the derivative of an e to the x function. V to the x, or v of x also stays the same because that's what product rule calls for. U of x now stays the same. And now we're going to take the derivative of this x cubed plus 7. So that turns into 3x squared, and the 7 goes away. So because it's not asking us for a function, honestly, my recommendation would be to just leave it like this because it'll inherently be easier to plug stuff into. But now remember, we have to plug in our x equals 1. So y prime of 1, which means I'm evaluating y prime at x equals 1. We're going to have 2e to the 1 plus, or times 1 cubed is 1 plus 7 plus again 2e to the 1 times 3x squared is 1. I'm sorry, 1 squared is 1, 3 times 1 is 3. So let's simplify that. We have 2e times 8, which is 16e, plus 3 times 2 is 6e, so that leaves us with 22e. And e is a number, right? So like pi, e is just some number. I believe it's something like 2.7, right? So that ends up being actually simplified to a number, even though it looks like it has a variable in it. So that's our rate of change following from a derivative function, right? So basically what we're going over in this video is reviewing why derivatives are so useful to us, because now we can understand what a function is doing at any point we care about. So that's why that's super important. If you learned something from this video, please like it. If you want to keep up to date with the videos I post in the future, subscribe to my channel and turn the notifications on. And then other than that, my recommendation is just to practice your derivative rules, because beyond that, it's just plugging in the value they give you. So keep practicing and best of luck.